In reality, no cosmic body ever moves strictly along a perfect ellipses. Deviations in orbital movements of planets from known Kepler's laws are always called astronomical perturbations. It was thanks to the detailed analysis of such orbital irregularities by scientists that the planet Neptune was successfully discovered. Periodic variations in the movement speed of a star allow astronomers to easily calculate the mass of an invisible distant exoplanet.
Welcome. You know, when we look at the cosmos, we often think of this perfect, clockwork mechanism. But what if I told you the most profound discoveries aren't found in that perfection? They're found in the subtle imperfections, the deviations from the ideal. Today, we are going to explore the physics of gravitational perturbations. Think of them as tiny cosmic wobbles, the tugs and pulls that cause planets and stars to stray from their predicted paths, and in doing so, they reveal entire worlds that we cannot see.
So here's our roadmap for today. We'll start with the foundation, the so-called Keplerian ideal of perfect orbits. Then, we'll dissect the anatomy of a perturbation itself. From there, we'll look at one of the greatest stories in science, the discovery of Neptune, a triumph of this very theory. Then we'll jump to the present day to see how we're hunting for invisible worlds around other stars. And finally, we'll consider what it all means to live in this universe of wobbles.
All right, first things first. To really understand a deviation, you have to first understand the perfect path. So let's begin by establishing our theoretical baseline, a simplified universe of perfect, predictable orbits. What you're seeing here is the essence of the two-body problem, which is really the starting point for all of celestial mechanics. We imagine a solitary planet orbiting its star, with absolutely nothing else in the universe to interfere. In this idealized case, its path would be a perfect, mathematically pure ellipse, repeating that same track flawlessly for all eternity. This theoretical movement is what we call unperturbed motion. It is our perfect model. But of course, reality is much, much messier. On the left, we have that ideal Keplerian ellipse. On the right, we have the real thing. You see, every object in our solar system is pulled on not just by the sun, but by every other object as well. Now, the total mass of all the other planets is a tiny fraction of the sun's mass, so these effects are small. But, and this is the critical part, they are constant and they are cumulative. Over time, they cause a real orbit to wobble, to precess, to deviate from that perfect ellipse. And that deviation is the perturbation. So, now that we have a sense of what a perturbation is, let's deconstruct it. Let's get into the physics of these deviations and examine the forces that are actually at play. We can classify perturbations into two main types. On the left, you have periodic perturbations. You can think of these as cyclical oscillations, a bit of a back-and-forth wobble. Over time, they average out, and they don't leave any permanent changes to the orbit's main characteristics. On the right, however, we have secular perturbations. These are different. These are slow, cumulative, one-way changes to an orbit's fundamental properties, like its shape or its tilt. And over millions or billions of years, it's these relentless secular perturbations that ultimately determine the stability and the fate of an entire planetary system. To really understand this force, we need to visualize it. So let's consider the classic three-body problem. We have the Sun, Sea, and two planets, P1 and P2. Now, for just a moment, let's imagine Planet 2 isn't there. In that case, the motion of Planet 1 is governed entirely by this single vector, the main gravitational acceleration, which points directly at the Sun. This force alone is what produces that perfect, unperturbed Keplerian orbit. Okay, now let's introduce our perturbing body, Planet 2. It brings two new accelerations into the mix. First, you have the direct gravitational pull from P2 on P1. That's the obvious one. But there is a second, much more subtle effect. You see, P2 is also pulling on the Sun, and because we are measuring all of this motion relative to the Sun, we're in an accelerating, non-inertial frame of reference. To account for this, we have to add another vector that's equal and opposite to the Sun's own acceleration from P2's pull. This basically accounts for the fact that the origin of our coordinate system is itself being tugged around. And this is the crucial point. The total perturbing acceleration is the vector sum of that direct pull and this indirect effect. And as you can see, the resulting force, the net perturbing acceleration, does not point directly at the perturbing planet. Its magnitude and its direction are constantly changing as the planets move through their orbits, which creates this extraordinarily complex and dynamic system. Now, all of this complex vector analysis is not just some academic exercise. In fact, we're now going to turn to its first and perhaps most spectacular validation, the discovery of an entire planet using nothing but mathematics. The discovery of Neptune is a masterclass in the scientific method. For decades, astronomers had a problem. Uranus was not where it was supposed to be. It consistently deviated from its calculated path. So Urbain Le Verrier and John Couch Adams independently came up with a bold hypothesis. These perturbations were being caused by a massive, undiscovered planet even farther out. They then used the incredibly complex mathematics of perturbation theory to calculate where this phantom world had to be. They essentially told astronomers, point your telescopes right here. And when they did, there it was, Neptune. This is why the event is so famously described as the planet discovered on the tip of a pen. Think about that. Neptune wasn't found by chance or by just randomly sweeping the skies. It was found because the rigorous application of Newtonian physics showed that these gravitational irregularities weren't errors at all. They were signals. They were whispers from an unseen world. And this powerful principle wasn't a one-time success. The very same methods that led us to Neptune have now become the workhorses of modern astronomy, and they're responsible for discovering thousands of planets orbiting other stars. The first method, radial velocity, actually looks for perturbations in the motion of the star itself. You see, a planet doesn't just orbit its star. They both orbit a common center of mass, a barycenter. This forces the much larger star into a tiny little wobble. As the star moves toward us in its wobble, its light gets blue shifted. As it moves away, it gets red shifted. By measuring this tiny periodic Doppler shift in the star's light, we can deduce the presence and even the mass of its unseen planetary companion. Transit timing variation is probably the most direct modern analog to Neptune's discovery. So imagine we're watching a planet as it transits or passes in front of its star. It should do that with perfect clockwork regularity. But if there's another planet in that system, its gravity will cause the transiting planet to arrive just a little bit early sometimes and a little bit late other times. By measuring these tiny variations, these wobbles in the transit schedule, we can detect and characterize a second non-transiting planet in the system. In very young star systems, we can actually see these perturbations in action. What you're looking at here is a protoplanetary disk, a vast disk of gas and dust surrounding a newborn star. A planet forming within this disk acts like a gravitational snowplow, carving out distinct gaps and creating beautiful spiral arms as it orbits. With incredible telescopes like ALMA and the James Webb, we can now directly image these structures. We are literally seeing the gravitational footprint of a planet in the process of being born. So, from the wobble of a distant star to a flicker in the timing of a transit, what's the ultimate legacy of all this work? It's nothing less than a fundamental shift in how we understand our place in the universe. The results really do speak for themselves. As of today, we have confirmed the existence of over 5,500 exoplanets, and the vast majority of them were not seen in the traditional sense. They were inferred. They were discovered by astronomers meticulously analyzing the tiny wobbles, the gravitational perturbations that they induce on their host stars or on their planetary neighbors. We have effectively learned how to listen to the gravitational whispers of the galaxy. And sometimes, these whispers become a symphony. In certain systems, planets can fall into what's called an orbital resonance, where their orbital periods are a simple integer ratio, like the 2-to-1 resonance you see here. In these cases, the gravitational perturbations happen at the same point in their orbits over and over again. This amplifies the effect and locks the planets into a remarkably stable, intricate dance, a true cosmic ballet. And this brings us to this central lesson. The universe is not a perfect clockwork machine. It's dynamic, it's complex, and it is full of these subtle imperfections. But it is within those very imperfections, a star that wobbles, a transit that arrives late, a gap in a dusty disk, that our most powerful tools for discovery lie. Which, of course, leaves us with the question, what other cosmic secrets are still hidden out there, just waiting to be heard in these gravitational whispers?
Thank you, friends. Strive for understanding and become wiser. See you soon.